Okay, so looking at organic synthesis. So we are going to begin with an introduction to organic synthesis. So organic synthesis is used to create organic molecules by design, and this is known as a synthetic route. Synthesis in chemistry allows professionals to produce molecules that are needed as drugs or materials. So basically, organic synthesis is all about how could we go from having an alkene as a starting material to ending up with a carboxylic acid. So how can we go from an alkene to a carboxylic acid? Or how could we go from an alcohol to an alkene? Or from a monohaloalkane to an ester. So it's all about how we go from one molecule to another. And to do that, we use reactions. So in the organic synthesis topic, the following reactions will be examined. So we've got our first reaction, which is an electrophilic addition. Now, for the most part, we can just call that an addition reaction. But specifically it's an electrophilic addition. Now we're going to look at that word electrophilic and what it means a little bit later on. But basically an addition reaction is a reaction in which a reactant is added to a multiple bond. Now multiple bonds are double bonds and triple bonds. Now double bonds and triple bonds are made from one sigma bond, and then a double bond also has one pi bond, and a triple bond has two pi bonds. So in an addition reaction, the pi bond is broken and sigma bonds are formed between the reactant and the atoms in the multiple bond. So for each of these reactions, I'm going to draw in a little diagram of an example just so that you can kind of see what's going on. So I'm going to try and make the examples fairly straightforward and fairly small. So what we're going to look at here is the reaction between ethene and bromine. So what will happen is our carbon to carbon double bond, the pi bond, will break, leaving a carbon to carbon single bond, the sigma bond. All of the hydrogens that are attached remain attached. Nothing happens with them. And then the bond between the two bromine atoms is going to break, and we are going to add one bromine onto one of the carbons that had the double bond, and the other bromine will be added on to the other carbon atom that had the double bond. So that's just a really straightforward, easy example. We will be looking at electrophilic addition reactions in pretty intense detail. We look at different types of addition. We look at the mechanism, so what actually happens during the reaction, and we also look at occasions in which addition reactions can produce more than one product. So there's a lot going to be happening around those addition reactions coming forward. Okay, our next reaction is an elimination reaction. And an elimination reaction is probably not one that we've really mentioned all that much up to this point, but that's a reaction in which atoms are removed from the reactant molecule and are not replaced, which results in the formation of a multiple bond. So atoms are removed from the reactant molecule and we get the formation of a multiple bond. So if we look at a little example of that, I'm going to look at the reaction of propan-1-ol, which is an alcohol. Now, in this reaction here, the OH from the alcohol and the hydrogen from a next door carbon are going to be removed. So these atoms here are going to be removed. And what we will end up with is a multiple bond forming in between those two carbons. Because those atoms have been removed and they're not replaced, that means the carbon atoms are having to form a double bond so that each of your carbons still makes 4 bonds. Now, all of the other atoms stay, they aren't removed. So it's just this kind of like bottom bit here that we've got the space created. That's where we've removed the atoms from. And then of course our other product in this reaction is going to be water, H2O. So that's what we would call an elimination reaction, and it is essentially the exact opposite of an addition. All right. Our next reaction is a nucleophilic substitution. This is a brand new reaction to advanced higher, and it is also a reaction that we look at in detail. Okay, so in a nucleophilic substitution, it's a reaction in which an atom or a group of atoms in a molecule is replaced by another atom or group of atoms. So, atom or group of atoms is replaced by another atom or group of atoms. Again, we'll look at this particular example in a lot more detail, but I'm just going to give you one wee example just now, just so you can see exactly what's going on. So I'm going to look at this molecule here. So I've got chloroethane. And I am going to react that with potassium hydroxide solution. Now I've popped the OH in blue because that's the group of atoms that's going to be substituted into the molecule, and it's just to make it stand out. So what's going to happen is the atoms in blue, the OH, they are going to substitute in place of the chlorine. Like so. And then we'll end up with KCl being our other product. So you can see it's just a straight substitution. Now we'll look at the different atoms that can be substituted and the mechanism behind how that works in a future lesson. Okay. All right. Now on to an oxidation reaction. This is no different from the reaction that we looked at higher. We looked at oxidation reactions of primary alcohols, secondary alcohols, and also oxidation reactions involving carboxylic acids. Involving aldehydes turning to carboxylic acids. So what I'm going to try and do, in fact, for this one here, I'm just going to pick one example. So what I'm going to do is I'm going to look at the example of a primary alcohol oxidizing to an aldehyde, and then I'll oxidize that again to a carboxylic acid. I'm not going to do the example for a secondary alcohol. That will feature at a later point in the notes. So let's take our simplest primary alcohol, which is ethanol. This will undergo an oxidation reaction, and to do that we use an oxidizing agent. We looked at various oxidizing agents at higher. We will refresh our memories on what those oxidizing agents are when we get to the correct part of this booklet, but for now we'll just say it's an oxidizing agent. So what will happen is our alcohol turns into an aldehyde. Now, if you've forgotten all about those functional groups, I'm going to be going through them all after we look at the types of reactions. So that's our aldehyde, and we can then use another oxidizing agent and we can turn that into a carboxylic acid. Like so. So we've got our primary alcohol oxidized to our aldehyde and then further oxidized to our carboxylic acid. And that process will use an oxidizing agent. And an oxidation reaction is an increase in the oxygen to hydrogen ratio of a molecule. So what we can see if we look at the oxygen to hydrogen ratio for each of these, in our alcohol, there's 1 oxygen to 1, 2, 3, 4, 5, 6 hydrogens. In our aldehyde, so after the oxidation has taken place, there's 1 oxygen to 4 hydrogens. So you can see the amount of oxygens to hydrogens has increased. That's a key indicator of an oxidation reaction. And then if we look at the carboxylic acid, we've got an oxygen to hydrogen ratio of 2 to 4 instead of 1 to 4. So we can see that again, the oxygen to hydrogen ratio has increased. All right, so then going on to look at the opposite of an oxidation reaction, which is a reduction reaction. And in a reduction reaction, there is a decrease in the oxygen to hydrogen atom ratio of the molecule. So we'll look at a little example for that. So I think for the reduction reaction, we'll take a ketone and we will reduce that into a secondary alcohol. Now, again, this is just an overview. Don't worry if you're thinking, oh, I've actually totally forgotten all about those reactions. It's not a problem. We will look at them again at the appropriate point in the booklet. So for this particular reaction here, I'm going to take my simplest ketone, which is propanone. Now, to do a reduction reaction, we use a reducing agent. Now, we will talk about examples of reducing agents in a few lessons' time. Reducing agents come up with regular frequency in advanced higher papers. They come up all the time. Right, so what will happen in our reduction reaction is we will convert the carbon double bond oxygen into a hydroxyl group, so an O to H, and then because we've broken the carbon to oxygen double bond, that leaves some space for another hydrogen to be added on. So we end up with something that looks like that. So again, if we look at the oxygen to hydrogen ratio, in our ketone, it is 1 to 6. And then in our alcohol, it's 1 to 8. So we can see that the oxygen to hydrogen ratio has decreased in our reduction reaction. All right, so in a condensation reaction, it's another reaction that we looked at higher. It's a reaction in which 2 molecules combine to form 1 larger molecule by eliminating a smaller molecule. So 2 molecules combine to form 1 larger molecule by eliminating a smaller molecule. There's lots of examples of condensation reactions, but just to keep things on the more straightforward side, I'll just look at a condensation reaction that we looked at from higher, which was an alcohol and a carboxylic acid condensing to form an ester. So I'm going to look at ethanol. And I'm going to react this with propanoic acid. Now, when you're doing condensation reactions, it is 100 times easier if the two functional groups of the two molecules face each other, because it's the functional groups that are responsible for the reactions of a molecule. So what I'm going to do is when I draw propanoic acid, I'm going to draw it so that the carboxyl functional group, that C double bond OH, is facing the hydroxyl group of the alcohol molecule. So there is my propanoic acid. This is a reversible reaction, so I'm just popping in that reversible reaction arrow. And in this reaction, the hydrogen from the hydroxyl group will combine with the OH from the carboxyl group, forming water and bringing what's left of the alcohol and the carboxylic acid molecule together. So we are going to end up with an ester that looks like this. So our first carbon in the alcohol with its 3 hydrogens is exactly the same. The second carbon has still got its 2 hydrogens and it's got the oxygen. However, that oxygen is no longer bonded to a hydrogen because that hydrogen has been removed in the water. Then if we go to the carboxylic acid molecule, the hydrogen and the oxygen from that carboxyl group have also been removed. So the next thing that we've got is a bond to a carbon double bond oxygen. That's then bonded to a CH2, and that CH2 is bonded to a CH3. And then our other product in this reaction is water, H2O. Okay. All right, so then looking at the opposite reaction to a condensation, which is a hydrolysis reaction. And that's a reaction in which a molecule is broken down into 2 smaller molecules by reacting with water. So for this particular example here, we're going to look at the hydrolysis of an amide to produce an amine and a carboxylic acid. It is a reaction that we looked at in the proteins part of the higher course, but I think it's probably worth doing as a wee example here just to remind ourselves about all of these different reactions that we looked at. So for this, we are going to start with our amide. I'm just keeping it really, really basic. So we've got our amide here. We know that's an amide because it's got an amide link, which is the C double bond O NH. Again, we're going to write all of those down on the next page, which looks at our functional groups. So we are going to react our amide with water. Now, what will happen is the amide link will break between the carbon and nitrogen single bond, and the water will break between one of the oxygens and one of the hydrogens. The carbon double bond oxygen will get the OH from the water to reform the carboxylic acid, and then the NH will get the remaining hydrogen from the water to reform the amine. So let's have a look and see what that would look like. So my C double bond O will regain that OH from the water, and then that NH will regain a hydrogen from the water to reform the amine, like so. Okay, right, so I believe that is the end of our reactions. So that's almost all of the reactions that we are going to be looking at Advanced Higher. I do say almost all. There are just one or two other reactions that are very, very small parts of the course that we'll talk about at the appropriate time. But pretty much every reaction that we look at is going to be an example of one of the ones that I've just discussed through with you. Okay. So being able to recognize those reactions is one of the most important parts of chemistry for Advanced Higher level. Being able to look at a reaction and say, oh, that's an elimination, or that's an addition, or that's a condensation, it's going to stand you in really, really good stead moving forward with the synthesis topic. Right, so let's continue with our introduction. So along with the reactions on the previous page, the following functional groups will be examined. So this is just going to serve as a little reminder of all the functional groups that we looked at National 5 and higher, and also to introduce a couple that are unique to Advanced Higher. So we're going to look at their names and their structures. So we're going to start with an alkene. Now, the name of the functional group in an alkene, it doesn't have like a fancy name. It's just a carbon-to-carbon double bond. And the structure of the functional group looks like that. So you've just got your carbon-to-carbon double bond. I've just popped on open bonds on the carbons. You could have anything attached to those. It could be hydrogens, it could be fluorines, it could be carbon hydrogens, it could be absolutely anything. We've then got an alkyne. Now, an alkyne isn't something that we've talked about up till now, but an alkyne is a carbon-to-carbon triple bond. Which will look like that. So we've got 3 bonds in between. Now, we did talk briefly about alkynes when we were looking at the molecular orbitals topic, and we talked about alkynes having sp hybridization. And we also talked about a triple bond being made from 1 sigma bond and 2 pi bonds. Right, on to our alcohol. Now, the functional group in an alcohol is a hydroxyl group. It's not a hydroxide, it's a hydroxyl. And that is an O to H. For our aldehyde, the name of the functional group is a carbonyl group. And a carbonyl group in an aldehyde is a C double bond O with an H that's then just attached to something else. Right, so for our ketone, it's also a carbonyl functional group. And for this, we've still got a C double bond O, and that C double bond O is in the middle of two other carbons, so it's not attached to a hydrogen. It's not found at the end of a chain, it's found in the middle. We then have carboxylic acids, and our functional group there is a carboxyl group. So you can see some similarities in the names between carbonyl and carboxyl, but they are different functional groups. And the carboxyl functional group is a C double bond O bonded to an OH. For our ester, the name of the functional group is just an ester link. And an ester link is a C double bond O bonded to an oxygen, like so. Right, we've then got an amine. And the name of the functional group in an amine is an amino group. Now, generally an amine will be an NH2, but we can have an amine that's just an N to H, or even just a nitrogen bonded to other atoms. We will look at the different types of amine when we look at amines a little bit later on in the topic. So for just now, I'm just going to draw that in as an NH2. For our amide, the functional group is an amide link. And the group is a carbon double bond oxygen bonded to an NH, and then there are other atoms on each side. And then finally, we have an aromatic. Now, the name of an aromatic functional group is actually called a phenyl group. That's not something we're going to see all that often, but it does come up from time to time. And that's when we have a benzene ring attached to another group of atoms. All right, so that is us now finished with what we are going to be actually looking at for today's lesson. The lessons that are coming up will, for the most part, focus on one of our functional groups. So, for example, we'll do a lesson that looks at alkenes. And in the lesson that looks at alkenes, we'll look at ways in which we can prepare alkenes. and we will look at ways in which we can react to alkenes. Now, the series of lessons on alkenes will probably be 3 lessons because we do a lot with alkenes. But then there will be other lessons that we look at, for example, with aldehydes and ketones, that will only take up 1 lesson because we'll look at how we prepare aldehydes and ketones and we'll look at how we react them. But there won't be much else there because there's not as much to actually have a look at with those particular reactions. So we'll be looking at these different groups kind of in detail in terms of preparation and reactions. There may be one, I think there's one particular group that actually isn't on this list, just because it doesn't have a specific name for its functional group, that we will come up with in a couple of lessons' time. Now, the most important thing for this topic is to just keep on top of everything. So go away and like have a look at each of these different functional groups, your types of reactions, maybe start to make some kind of like revision flashcards or something, or just actually study them and make sure that you're familiar with all of these groups, because that's what's going to be what will help you going forward. Okay, now if you have any questions at all about anything that we do as part of these lessons in particular, please get in contact straight away. Just because there is so much in this topic, it is a huge topic. It's better to just get help sooner rather than find yourself overwhelmed a wee bit later on, because you will find that although it's a large topic, there is a good deal of repetition that does kind of come up when we're looking at our different reactions. So if anybody has any questions,